Okay, imagine you're in a car. You look down at the speedometer. It says 60 kilometers per hour. Here's the weird part. Per hour means over an hour. But you're not driving for a whole hour right this second. You're driving for this exact tiny moment. So how can you have a speed at a single moment in time? That one little question, that exact question, took smart people almost 2,000 years to figure out. And the answer? It's the most useful idea in all of math. It's called a derivative. By the end of this video, you're going to understand what that word actually means. Not how to compute one, just what it is. And I promise, no scary symbols until you're ready for them. Let's start with something you already know. Average speed. If you ride your bike 100 meters in 10 seconds, your average speed is 10 meters per second. Distance divided by time. Simple. But here's the thing. You probably weren't going 10 the whole time. Maybe you started slow. Then you went really fast in the middle. Then you slowed down at the end. 10 is just the average. It hides what was really happening at each moment. Now here's the real question. What if I stop the video at exactly the 5th second of your ride, not before, not after? How fast were you going right then? You can't just say 10. That's the average for the whole trip. We want to know your speed at that one moment. And here's where it gets tricky. Because how do you measure speed at a single moment? A moment has no time in it. 0 seconds. And if you go 0 distance in 0 time, that's 0 divided by 0. Math doesn't like that. So we need a clever trick. Here's the trick. And honestly, it's so simple it almost feels like cheating. Instead of trying to measure speed at one exact moment, which is impossible, we measure speed over a tiny little stretch of time near that moment. Just 1 second. We see how far we went in that 1 second. Distance divided by time. We get a speed. It's not perfect, but it's close. Now watch this. We squeeze the time stretch smaller. Half a second. A quarter of a second. 100th of a second. The smaller we make it, the closer our answer gets to the true speed at that moment. We never quite reach a single instant, but we get as close as we like. That idea, getting as close as you want, without ever quite touching, has a special name. It's called a limit. And a derivative? A derivative is just a limit doing one specific job. It's the limit of how steep a line is between 2 points, as those 2 points get squeezed closer and closer together, until they're basically the same point. I know that sounds abstract, so let me draw it. Let's draw a smooth curve. Doesn't matter what this curve actually is. Just pretend it's a hill. A ball is rolling down this hill. The further right we go, the higher and faster things get. Now I pick one point on the curve. Right here. Question. How steep is the curve at that exact point? That's basically asking, how fast is the ball changing right there? To answer that, I need to know the slope at that point. And quick word about slope, since we're going to keep using it. Slope just means how tilted something is. A flat road has no slope. A steep hill has lots of slope. That's all the word means. But here's the problem. To measure slope, you need 2 points. I only have one. So I cheat. I pick a second point on the curve. Nearby. I draw a straight line between them. That line has a slope, and we can actually measure it. Count how much the line goes up. Divide by how much it goes sideways. Up over sideways. That's the slope. Easy. But it's not quite right. The line cuts through the curve. It's only a guess at how steep the curve is at our first point. So I do the trick. I slide the second dot closer to the first one. Closer. Closer. And as the second dot gets infinitely close, basically touching the first one, the line stops cutting through the curve. It just kisses it. At exactly 1 point. That line has a name. It's called a tangent line. And its slope, how steep that tangent line is, that is the derivative. That's it. Honestly, that's the whole big idea. A derivative tells you how steep a curve is at one exact point. We use the trick, sliding 2 points together, to get a slope at a single point. Something that should have been impossible. If you got that, you got the heart of calculus. The rest is just learning shortcuts to do this quickly. Quick thing. If this is starting to click for you, hit subscribe. I make these as clear as I can. The channel grows when you do that one tap. Okay, back to it. Let's do one with actual numbers. So this isn't all hand-waving. Imagine you throw a ball straight up in the air. Its height, how high it is, changes with time. Goes up, slows down, falls back down. Smart physics people figured out, if you throw a ball up at 20 meters per second, its height after a few seconds follows this rule. Height equals 20 times t minus 5 times t squared. The t just means how many seconds have passed. Plug in any time, you get the height at that time. Now I want to know, how fast is the ball moving at exactly 1 second? So we use the trick. We look at the ball's height at 1 second, and then at a tiny bit later. Let's call that tiny bit h. Just a letter for how small. The average speed across that tiny gap is the change in height, divided by h. Now I plug in the rule and crunch it. I'll go slowly. Don't worry if you don't follow every line. Just watch the shape of what happens. After cleaning up, the average speed across the tiny gap is 10 minus 5 times h. Whatever the tiny h is, that's the answer. If h is 1, the speed was 5. If h is a half, the speed was 7.5. The smaller h gets, the closer the answer gets to something specific. Watch what happens when we shrink h to basically nothing. As h gets closer and closer to 0, the answer approaches 10. Exactly 10. 10 meters per second. That's the ball's speed at exactly 1 second after you threw it. We just did calculus. That's it. We took an impossible question, speed at a single instant, and we answered it. In math shorthand, this gets written as h prime of 1 equals 10. That little tick mark next to the h just means the derivative of. It's a shortcut for everything we just did. Don't be scared of it. You already know what it means. Okay, so we can find the steepness of a curve at any point. That sounds like a weird party trick. Why does anyone care? Because almost everything in the world is a curve. Your phone's GPS uses derivatives to guess when you'll arrive. It looks at how fast your position is changing right now and predicts. Doctors use derivatives to check your heart rate. The rate your heart beats is literally a derivative. How fast your heart's count is changing. Engineers use derivatives to design every plane, every bridge, every car. They need to know how fast forces are changing, not just averages, exact, instant forces. Money people use derivatives to predict markets. How fast is a stock price changing right now? That's a derivative. And here's the wild one. Every machine that learns anything, every AI model, every voice assistant, every recommendation that knows what you want runs on derivatives. Millions of them. Every second. That tiny idea, figuring out how fast something is changing at one exact moment, built the modern world. That's not an exaggeration. It actually did. So, let's pull it all together in plain words. A curve has different steepness at different points. To find the steepness at one exact point, we draw a line between that point and a nearby one. Then we slide the nearby point closer and closer until they're basically the same. The slope of that final line, the tangent line, is the derivative. That's the whole story. If someone ever tries to scare you with calculus, just remember the speedometer. You knew the answer before they showed you the formula. Now, if this was useful, the best thing you can do is hit subscribe. Honestly, the channel only grows because people who got something out of a video click that button. So if I earned it, please tap subscribe. In the next video, I want to dig into what limits actually are. We use them today like a magic trick, but they have a beautiful logic to them, and once you see it, calculus stops feeling like magic and starts feeling obvious. That's coming next. Thanks for watching. See you in the next one.